had a nice evening after the dinner last night, and so it's good that you're here. Very good. Yeah, so I was just commenting that you have to avoid the region of, there's a stadium called Allianz Park in the neighborhood, not too far from here, and you should avoid it because there's a concert of Taylor Swift this tonight. It's going to be completely packed. So yeah, try to avoid that. Or you can go to the concert, and it depends. Of course, tickets should be sold out, but yeah, avoid that. Okay, so now we are going to have the fifth and final last lecture of Professor Laine. So please, Mikko.
Yeah, thanks. Yeah, so I'm also happy to see so many still here after all these lectures. So yeah, so today we come then a bit, yeah, in sense closer to the main topic of this school. And let me start by kind of redrawing one of these cartoons that we had before. So what, roughly speaking, could happen as a function of time. And so now I take here then the density of baryon plus lepton number. And then we put somewhere a moment of a phase transition. And so really the idea of electroweak baryogenesis is that there are two regimes in which something nice happens. And the first nice thing is actually here very early on. And the nice thing is that whatever initial conditions we take, they go away. That's very satisfying. That's what we, then we are not sensitive to some unknowns. So you start from somewhere, and just by the same dissipative dynamics that we had before, it should go towards zero, and then it can fluctuate around zero. And really, it doesn't matter even which sign you take. You can start from anywhere, and it goes to zero, and then it oscillates. Okay, so the idea then is that so in this regime, we have this some rate, time, and gamma b plus L is much larger than the Hubble rate at this time. And so we'll come back in a second on to why it's like that. And then we have the phase transition, and somehow this complicated dynamics, the system is kicked up or down, and if we are lucky, it's kicked in the right direction. Say that we get a positive baryon number, if, well, as that is what we want. And afterwards, in principle, the same dynamics continues, but now we hope that the rate then is so small that even though it's in principle there, then by today, it doesn't do much. So again, in principle the same, but now gamma b plus L should be much less than h. So that's really what we need. This rate and a very non-trivial behavior of this rate, and then a non-trivial behavior here. Okay, so now a bit about this rate. So let me first actually write the equation. We have kind of seen some version of this equation already and discussed this it a little bit, but I think we didn't see the full equation yet. So it's the b plus L anomaly equation. And so the equation says the following, that if I take the divergence of the current, and so now I sum over all generations, n, g is the number of generations, and then I take quarks of each generation And then I take leptons of each generation. And these are doublets, and these are doublets. I should have maybe put this one here. And here there is no, I mean, we talked a lot about left-handed, right-handed, but here there is no left-handed, right-handed. These are really the full quarks, the full leptons, and the divergence of the current. So this is then the baryon part, and this is the lepton part. Okay, so the chiral anomaly equation then says that this is non-zero, this is not conserved. It's not conserved if we have some gauge field background. And what it then is well, all the generations, they kind of couple to the same, so this sum over the generation, it factorizes, and then there is some numerical factor, and then there are really two terms. There's g squared fa, and epsilon. Epsilon mu nu rho sigma g squared fa mu nu fa rho sigma, and then minus g prime squared minus g prime squared b mu nu b rho sigma. This is the SU2 left part, and this is the U hypercharge one part. Okay, we heard a lot of some arguments about topology and why that means that this SU2 part is the important part and the U1 part is not important. Actually, today I will show that the U1 part is also very interesting and it's important for some things. And so this is really the full equation. But this is the one which then has more properties, a special property, which is why then usually one at least first discusses this. And this is the important thing for the P plus L. Okay, so now that's the equation, nice to write, looks nice. However, I mean, what we are really interested in is not this equation itself, because really the right-hand side depends on the gauge fields. And the gauge fields, they are not some fixed fields. I mean, we still have to also, they have dynamics. And it's the dynamics of these fields which somehow is responsible for how the B plus L is violated. We just see from this that it's non-zero. But what it exactly does, the right-hand side, it's not at all trivial to from this equation to really derive this, like this gamma. That's what we would really want. So let me just maybe even write it explicitly, that how to get gamma B plus L from here is non-trivial. And I will also not show it. It's not trivial enough that I would not be able to show it in one lecture. I don't know if I would be able to show it in a whole week. If I only concentrated on this, maybe. But even then, it's kind of, yeah, a little bit sort of advanced non-equilibrium quantum field theory that one needs to do. So we will not do that. We will do something else today, which, however, is which is much simpler, but in a way it is related to this dynamics. But before we get there, I will still give the results. I will show the results and discuss them a little bit. So the first thing that we needed is that this gamma P plus L at very high temperatures, 100 GeV, that it is larger than the Hubble rate. And so now there was a lot of work on this quantity some, I don't know, 20 years ago or so. It was a hard problem to settle. In fact, it was a hard problem to settle even to see in which power of the coupling it scales. Alpha is the coupling that we had also yesterday. And yesterday we could draw some Feynman diagrams for producing gravitons, and then from that we could really take an amplitude square and we could see which power of alpha appears. So here appears actually a very high power of alpha to the 5th. So I mean, at least from here one should be able to anticipate that the reactions must be somehow complicated because you need so many vertices. If you put too few vertices, then for some reason, which is not obvious here, the result is 0. So lots and lots of vertices are needed, and then T. At high temperatures, the Higgs wave is 0 or very close to 0, and then basically the temperature is the only scale. And so it scales with T. Then there is some numerical prefactor here, which I will not put in there. Also, there is some log here. I think Misha put here some log, but I omitted the log. So this is the number, and the difficulty is that there is a numerical factor here, and actually this numerical factor, even though I'm assuming that the coupling is small, then the numerical factor, it is even, not only do you need many diagrams, you need actually infinitely many diagrams, and you have to sum them in a certain way. To put it in another way, this prefactor is non-perturbative. This is it's one of the, and this is we often talk about infrared problems, and this particular problem is infrared problem of thermal field theory, of non-abelian thermal field theory, but also one specifically is known as the Linde problem of thermal field theory. But it doesn't mean, I mean, the theory itself is well defined. It's just that to work out something, you need to work really hard. You need to formulate things well and then figure out what comes out. Anyway, this work has now been done. And what we can now do is we can compare this with the Hubble rate. So we want this to be I'm claiming that this is larger than the Hubble rate. We want this to be larger than the Hubble rate, so let's see when that's the case. This is the rate. Hubble rate was T squared over Planck mass. And so we see that this is the case if temperature is much less than alpha to the 5th times the Planck mass. So again, a huge suppression, because numerically, G, the weak coupling is like 2/3, then it takes squared 4/9, and then 4 cancels. So 1/30 is sort of the order of magnitude. And so 5th power of 1/30 is a small number, but the Planck mass is a very large number. And so if this were so it's not quite 1/100. If it were 1/100, we would get 10 to minus 10, but it's not quite, so let's say 10 to 10 GeV or so. Anyway, a very high temperature, much above this temperature. So very early on, this rate is very, very fast, and indeed initial conditions go away. Okay, so then there is the rate at temperature less than temperature less than 100 GeV. Actually, however, non-zero. Still, it shouldn't be 0 to get what I show here. And in that regime, There, the computation is the computation that one sees these plots. We've seen many times this plot. One sees this some kind of a landscape of barriers, and one talks about going above the barrier, and in this regime, then the configuration is a saddle point of the type that we were discussing. So this is now. What is this? This has the structure which is exactly the same as what we were discussing with the nucleation. So some free energy goes over temperature. There's a prefactor. Of course, one needs also the prefactor. This has a dimension of GeV. There's a prefactor. Prefactor is very much harder to compute than this exponent. But there's also work on that. At the end of the day, there are also simulations on that. So something is known about that, but not as much as about the exponent. But maybe the exponent is the most important thing, and the exponent then that's then what we call the Sveileron energy. Again, it's really free energy. And so this has also a bit funny form. It's 2 times mw over alpha. So funny, because actually here alpha is downstairs. In perturbation theory, again, if you do perturbation theory, how on earth could you get alpha down? Well, you cannot get alpha downstairs. In the vertices, there is alpha, so you get always a positive power of alpha. If you get 1 over alpha, this is a characteristic that you have solved really some saddle point equations and evaluated that numerically. And solving the saddle point and having some action for the saddle point, for the bounds, that is, in a sense, that is a non-perturbative evaluation of something, and there one can get 1 over alpha. This is not the exact result. There is also a function here which depends on the lambda, on the quartic coupling of the Higgs. So one often writes it then as a function of the Higgs over W mass. And this function is not known analytically, it's known numerically, but it is of order. It's kind of, the normalization has been so chosen here that this number is of order unity, if you take the Higgs mass to the physical value. So now one sees, and we remember that the W mass is G times the Higgs wave over 2. And so we see that if, so we see that this is sort of, maybe we G over alpha, 2 over alpha, G V Higgs wave over 2 times phi. These cancel. This is 2/3, and alpha is 1 over 30, so 30. So some number like 20 times and the phi. 20 times the wave. And now what we see is that if the wave is large compared with the temperature, then this becomes very, very small. And so now, to make a quantitative estimate, we would take this expression, we would put it here, and then we would have to argue something or estimate somehow this prefactor, and then we compare it with the Hubble rate. And so it's a bit of a dirty game as long as one doesn't know too much about the prefactor. But fortunately, the prefactor is not so super important because this is an extremely rapidly varying function, e to minus 20 volume v over t. So it kind of depends very rapidly on the v over t. And so we get kind of a reasonable estimate, namely that gamma b plus L is much less than h, corresponds to v over t larger than 1 point something. And now the point, what exactly it is, then one would have to be more careful. But usually one just says larger than 1. So this is now what, for purposes of baryogenesis, what we then call a strong transition. If we satisfy this criterion, because then we are in business. Then the rate is small, and then whatever we produced can stay there. Okay. So now that's the picture. So now, I mean, as you see somehow, well, it's a beautiful picture in the sense that one doesn't need anything more than the standard model, and there are all these subtle effects and non-perturbative physics in the weak interactions, the thermal system. But, well, let's say the backside is that one really needs, there are many spots where one cannot do a concrete computation. One rather needs intuition or a good order of magnitude estimate or simulation. So it's kind of difficult. It took many decades to make this quantitative. So what I want to do today now, in the remainder of the talk, I will do kind of another exercise, which is simpler, but somehow kind of shows some ingredients of this in a concrete way. Okay, maybe before going that, is there some questions about this general setup?
So I think you just visited, but what is phi there?
This phi.
Yeah.
This phi is some function which comes from solving numerically for the saddle point.
Okay.
You have to solve it numerically. The equations are non-linear, and there's no analytic solution. So you solve it numerically, and it's depends on the quartic coupling. We reparameterize the quartic coupling with this ratio, and yeah.
Okay, thank you.
Okay, so now we will do the following question. Suppose we don't know about all this fancy physics. If we didn't know about the anomaly, what would we do? Then we would say that baryon number is conserved. Then we would also say that the lepton number is conserved. Actually, I will make life a little bit more interesting for reasons that will then become apparent. I will assume that the lepton number is conserved actually separately in each generation. K is my 1 over ng. Why is that? Well, we know in the leptonic sector, I mean, today or at low temperatures, one can convert leptons to each other via neutrino oscillations. Neutrinos oscillate to each other. At high temperatures, the neutrino oscillations are not really very effective, and so therefore lepton numbers in the separate generations, they are effectively conserved. But I will make a further assumption, which is I will assume that separately the lepton number of left-handed and right-handed lepton is conserved. That has to do with, well, it's a little bit also related to the Yukawa couplings, and well, like electron Yukawa coupling is very small. Yukawa couplings always connect left and right components, as we've seen. But if the Yukawas are very small, then maybe the transformation from left to right is not very effective. In the quark sector, Yukawas are larger. There's a CKM matrix. Everything goes to each other. Also in the strong sector, there are what are called the Strong's ailerons. So it's a similar process. Actually, we saw the equation. So it's a violation of the U-axial anomaly, and that converts left-handed quarks to right-handed quarks. And these processes are also in equilibrium in a large temperature range. So there we don't make this assumption. So suppose we were very naive and we thought that let's take this maximal set of things. If we assume that these are conserved, then what we would have to do, what statistical physics tells us, is that when they are conserved, then there's no argument why they should dissipate to zero in the beginning. If they are conserved, they are conserved. And in statistical physics, this means that we should assign chemical potentials to these guys. And chemical potentials I denote by mu. KL, K right. I should put here mu b. Often I put mu quark num, but it's proportional to the mu b, but somehow it's a somehow kind of a convention very often that people like to use the quark chemical potential then. Okay, so suppose we introduce these chemical potentials and now the question is, we do this and then we apply our tools. I mean, tools that I've in principle introduced to you. We try to do the thermodynamics of this system. We try to compute, for instance, the free energy density. So as a first step, we try to compute dimensionally reduced effective action and then study what its properties are. We construct the effective action. And so now what is the question? Question is, suppose we do this, we are naive, we do this, like in textbook, we compute this thing. And the question is this formula strong enough to show that something goes wrong? Basically, that's the question. What could go wrong? Okay, so to get there, maybe I use this equation to write alternative representations of this. We saw it also, so one can write this sum from 1 to ng is the same as ng. Number of generations, 3. And then there is some conventional factor, which I think would here put the factor of 2. And then if these are smooth gauge fields here, then one can write them as derivatives, d mu. And this one gives k mu. I think we saw this d mu, k mu already. And then I put here an index 2 for the SU2, and then there's a k mu 1 for the U1. And in particular, K0 of I, 1 or 2, is called Chern-Simons density. Chern-Simons number would be the integral of this density over spatial volume. I think I will want to often write it as n Chern-Simons to be reminded of what it is, and then SU2 or SU1 or U1. Okay, so that and I'll give the expression in a moment, but that is kind of as an anticipation that it's really Chern-Simons number is related very much to the structure. It's the density that you get if you represent the right-hand side as a divergence. Okay, so now what could go wrong? So what do we do? So chemical potential, be reminded what does it mean. It means that we are computing something like a partition function, and then we put here, in addition to Hamiltonian, we put a chemical potential. Or if there are many chemical potentials, like in my game, we put chemical potentials to each conserved quantity, and then we put the corresponding number operators here. And so now for fermions, the numbers are simply integrals over space of psi bar psi and the gamma zero. That's the zero component of a vector current that gives me a charge. So now I couple it to this one. So it just, you see that it remains quadratic in fermions. Doesn't change the field, appearance of the field, but it somehow modifies with what happens with time derivatives, so to say, in the Feynman rules, because it appears with gamma zero just like time derivatives appear with gamma zero. And so it's a simple modification of the Feynman rules. In fact, it's a nice little exercise to show that in this imaginary time formalism that what I've been using, then this means that the Matsubara frequencies that we had, they get replaced by omega n plus I times this mu. Mu I. It's kind of a shift of the Matsubara frequencies, and then that changes the results, and that changes the partition function. Okay, now, what's important about introducing this mu? Okay, so it modifies the Feynman rules, but importantly, it also changes it breaks symmetries. So these chemical potentials, they break explicitly what? Well, charge conjugation. I mean, that's the reason, that's what they're supposed to do. In relativistic field theory, chemical potential means that you couple to a symmetry. I mean, charge in relativistic field theory is particles minus antiparticles. And if it's non-zero, like baryon asymmetry, baryons minus antibaryons. If it's non-zero, you break charge conjugation. These break C. And so somehow from the point of view of field theory, this is always an extremely interesting appearance. When you break symmetry, then it implies, and you are constructing some kind of an effective field theory, then breaking some symmetry implies that you can have new operators. Because the way that we construct effective theories is we first write down all the operators, but in so doing, we assume the symmetries that we have, and we make use of all the symmetries to have as few operators as possible. But if the underlying symmetry is smaller, we have more operators. So what we then have to do is we have to recompute basically all the diagrams. So we computed with a scalar field theory. We computed one of these diagrams with just a bubble, like a mass correction to the scalar field. Now we are looking at a system which has not only the scalar field, as fermions, it has gauge fields. And And since we introduced these chemical potentials for the fermions, then we have to look at some fermionic, well, there are fermionic loops. So fermion, but in addition, well, okay, non-zero Matsubara frequencies, that's anyways the case for fermions, so I don't even need to write it down. And then we couple these to fields. And now in particular, actually we can couple it to a single gauge field or 2 gauge fields or any number of gauge fields or scalar fields. You may remember that in this dimensional reduced effective theory, there are no fermions in the action, because the fermions always have this non-zero Matsubara frequency. It's only bosons that we need to have in the effective action. So bosons either gauge fields or scalars. I will not write down the scalars because the interesting effects really come for us, they come now for these gauge fields. Now we will not do these loops, but let me show what they do. So L effective now with the chemical potentials has the form the old one. Actually, to be precise, old with modified parameters. That's one thing that can happen, that you don't generate a new operator, you generate an old operator, but the parameters can get modified. That's important quantitatively, but it's not important qualitatively for us today. But then there are new operators. Actually, it's quite interesting and looks very weird at first sight, but even this term, if you have chemical potentials, this term is non-zero. It gives an operator like this, I times then some coupling, J3 coupling, and then B, the abelian field, and the zero component of the abelian field.
I'm a little bit confusing about the first contribution, because usually in quantum field theory, some kind of bubble, closed bubble, don't contribute to the real amplitude. Why here is contributing? Because
it's not. Yeah, it contributes to this term. So it contributes to the term. So first of all, this is the coefficient. This is proportional to the chemical potentials. You wouldn't have this term if you had, this is proportional, not alpha, it's proportional. Normally, often we look at non-abelian fields. If you want to write a similar term for a non-abelian field, you would have to, it would be a matrix. You would put like a trace of a matrix. But for non-abelian field, the trace of a matrix is 0. So this is something special for abelian fields. Also, you see, this is gauge invariant. Why is it gauge invariant? Because we are looking at static fields. And for an abelian field, gauge transformation is B mu minus d mu theta. But if we are looking at static fields, then also gauge transformations are static, then this term is not there. So this is a gauge invariant field in this effective action. It has odd symmetries, but that's still fine because also the coefficient is proportional to these chemical potentials. It's only there for abelian field. So it just is there, but it's not a scattering amplitude. What this kind of a linear term does is you can try to imagine that then you search for the ground state. And if there's a linear term, it means that your ground state is not 0. It kind of shifts the ground state a little bit away from 0. So, and this is fine because you know from electrodynamics that if you put charge in a metal, in a body, then the body gets a potential, electric potential. And this is just the electric potential. If you put the chemical potential, you mean that we put the charge there, and the charge means that the charges kind of repel each other, that they go on the surface if it were a finite volume, and inside there is the potential. It's the usual electrodynamics that the charged body has a potential. That's what this physics is. So it's interesting physics, it's electrodynamics, but it's not very important for us today. So actually, I didn't want to discuss this too much. But it's indeed fun because it's something that you wouldn't expect to see. Okay. So the important thing is what comes from the other terms, and I will just write down the results. And the result, there are actually, well, two terms that are important. So the first term, which is important, has 3 times number of generations times quark chemical potential plus sum over generations and the chemical potentials of the left-handed leptons. This kind of a term, and it multiplies something. It multiplies something which is effectively what we saw here. So there was SU2 part minus U1 part, and then this whole thing one could write down as a divergence, and the zero component of the current was Chern-Simons number. So now we are not in the 4-dimensional theory, we are in this 3-dimensional dimensionally reduced theory, effective theory, and what appears here is then, in fact, is not FF dual, it is the Chern-Simons terms, N CS2 minus N CS1. But it really has the same structure. Okay, then there is another term which has left-handed minus right-handed chemical potentials for the leptons, and this has only the U1 Chern-Simons term. So now the question is there something wrong now? I mean, what question was what could go wrong? Is there something wrong with these terms? So, in fact, there is something wrong. There's something wrong with this first term because problem is that this FF dual is gauge invariant. But if you take the divergence and you identify the Chern-Simons density, then it is not gauge invariant. Well, to be precise, it's not gauge invariant in what are called large gauge transformations. But I mean, our theory doesn't matter if the gauge transformation is small or large. If we start with the standard model, if we build it upon gauge invariance, and then we do some computation, and then we find a result which is not gauge invariant, then somehow something is not right. Well, obviously one could talk about this for a long time. But what it means at the end of the day, how can we get rid of this problem? Well, there's a simple solution to this problem. And the solution is that the coefficient of this problematic term must be 0. And so this means that this coefficient must be 0. And this means that the quark, and thus the baryon density, is not independent of the lepton densities. They must be related. So usually we talk about always baryon number, lepton number, but actually this what we obtain here, the real this is the real constraint, a constraint which is valid, including interactions. This is not a tree-level constraint. It comes from all these loops, and actually it is really valid to all orders in perturbation theory. This is the real kind of precise statement that we mean when we say that B plus L or NB plus L is 0. Why is it the same? Well, because if one then computes the number density, then for small chemical potential, the number densities are proportional to chemical potential. So then one can, in some limit, one can convert this to this, but this is more correct, so to say. Yes, I mean, you have to work it. It's not obvious, maybe at first sight, you have to work it out, but we'll come to that. Actually, we'll kind of see a glimpse of that when we look at this term. So let's come to that term now in next. Anyway, this is the first important lesson. That indeed, somehow, even if we didn't know about this, and then we do just a careful computation, no magic, just some loops, and then we get a result, and we think about the result, then we see that something is not right. So now how about the other term with the abelian Chern-Simons term? So I didn't write it yet, but let me write now. The abelian Chern-Simons term is G prime squared over 32 pi squared, and then epsilon. So this lives only in spatial dimensions, and so I have an epsilon, but I have the three index epsilon, and then bi b jk. I put all the indices down because everything is spatial, so there are no minus signs also, and it's a bit simpler to write when things are down, where this one is dgbk minus dkbg. Okay, so now let me say that this one is gauge invariant. So the gauge transformation would be bi goes to bi minus di theta, some gauge parameter. And if we look at what happens, then the field strength is always gauge invariant, but here is an appearance of the gauge potential. So that's not obviously gauge invariant. Well, the first term gives the same. But then from here I get minus di theta epsilon ijk b jk. And now what I do is so it's not obviously 0, but we can write this term as I can write it as I kind of do, so to say, partial integration, so write it as a total derivative. And then I have to correct because this di can act here or here, but here it acts only there, so I have to subtract minus theta epsilon ijk di bjk. And this term I can write as these indices are summed over, of course. I can rewrite it as a to a permutation of the indices. So then it's, if I do a symmetric permutation, then the epsilon stays the epsilon. di bjk, dj bki, dk bij. And now if one inserts here, if I insert here this expression, then there are always two terms, and half of them come with a plus sign and half of them come with a minus sign. And if I take all the derivatives, then all these terms, they nicely cancel. So this term is 0. Okay, this term is a total derivative, so it is not 0, but it's the total derivative. But I think now we come a little bit back to also to what this topology. I mean, with an abelian field, there is no for abelian fields we should certainly take boundary conditions such that the field strength, which is a physical quantity, it is 0 at asymptotic infinity, and so boundary terms should not matter. And so it is gauge invariant up to a boundary term, but in an abelian case, boundary terms should not matter. Okay, so good. So it's gauge invariant, and so we cannot just say that it cannot exist. So now let's do the following. Let's accept this term. It's there, we cannot say 0, and see what it would lead to. So now we have to work a bit harder, see if it has some significance. I don't want to always write this combination, so yes?
So we were talking about large non-trivial gauge configurations in the past. So how are we ignoring this term just because it's a total derivative? So.
Because a total derivative, and this is abelian, and this is field strength. I mean, this is abelian. So in the abelian case, there is just this is field strength. In the abelian case, the field strength really is a physical quantity, gauge invariant. It has to go to 0. Otherwise, you have energy at infinity. I mean, energy of an abelian case, energy is proportional to the field strength squared. This really has to go to 0.
I see. Thank you.
So denote. So I take a C. I put all the coefficients somehow in the what we had is G prime squared. 32 pi squared, and then the coefficient was 2 times the sum over generations. K left minus K right. And what I want to do is, okay, I have this action, I have an additional term, so let's try to like look for like a minimum of the action. So solution of equations of motion. That's now like not some subtle point, but really like the minimum. Like what is the ground state, if you wish. Now I will, however, do this in a bit funny way, and namely I will now go back to Minkowskian. I will allow for time dependence. And so this, why I do this is, it will then become clear, but I'll now consider like a Minkowskian Lagrangian, so minus b mu nu, b mu nu, but then I add this term. There's always this, okay, minus sign in between the Euclidean Lagrangian and the Minkowskian, so I should put it with a minus sign. So minus c epsilon I j k di b j k. You might now, at this moment, you might protest that this looks Lorentz invariant, this is not Lorentz invariant. Actually, one can rewrite this, one can generalize this, one can rewrite it in a way that at the end of the day you can make a Lorentz invariant Chern-Simons density, but it's not necessary for, I mean, it doesn't change the key point, and it's a bit complicated, so we don't do it. We just add this term. So now, look at the equations of motion. Equations of motion, we take this and we take the Euler-Lagrange. So well, simpler to write, just ds dB. We kind of look for the minimum equations of motion. It is relatively simple because this is, these are linear in the fields. Both of them are linear in the fields, so it's quadratic, and this is quadratic. So really, this action is quadratic. There are no interactions there. It's like a free theory, but with an additional term. Okay, so now, now this is a nice exercise. And I leave it as an exercise to fill in the intermediate steps, but let me show what comes out, or how one best does it. What's the simplest way to do it is that we can always choose a gauge, gauge. We choose a gauge which is kind of decoupled from our okay. I can choose a gauge where the zero component is zero. It's a partial gauge fixing. I'll go to a mixed time momentum representation. That means then the spatial components I'll write as Fourier integrals, but only in spatial momentum, and then like a mixed, depending on real time, and then momentum minus ik dot x. Now, this depends on momentum. It's to make it simpler, I'll choose a frame with where my momentum points in the z direction, 0, 0, k. Okay, these are relatively simple things to do, and let me just show what the equations are that one gets. So if the momentum points in the z direction, then the physical components are the transverse components, like in electromagnetism, B1 and B2. And what this term does is, you see there is epsilon ijk, so somehow the indices are necessarily different. So it mixes the B1 and B2 in a funny way. And so what comes out is that the time derivatives, I therefore write it as a matrix equation. And what comes out is then minus k squared minus k squared. If you didn't have anything else, then we would get a normal oscillation. D squared B1 is k minus k squared B1. We would get the cosine and sine normal oscillations that we expect. But now there's an additional term here, once with the minus I c k, once with the plus I c k. It's mixed system. Well, what do we do with a mixed system? We diagonalize it. It's a 2 by 2 system. We can diagonalize it. To diagonalize it, we have to search for the eigenvalues first. So let me denote by lambda the eigenvalue. So as usual, I then subtract here lambda, and I take the determinant. So minus k squared minus lambda squared, and then minus is plus, but then it's an I, so in total it's minus 16 c squared k squared is 0. That's my eigenvalue equation. So lambda squared plus 2 times lambda k squared plus k to the 4th minus 16 c squared k squared is 0. So now we have to solve for the eigenvalue. So therefore lambda is minus q over 2 minus k squared plus minus q over 2 squared k to the 4th minus the constant minus k to the 4th plus 16 c squared k squared minus k squared plus minus 4 times c times k. I mean, a little bit like in the matrix, but without any i's. These are real eigenvalues. It's a Hermitian matrix. These are real eigenvalues. So let's plot the eigenvalues as a function of k. The first term is this minus k. If c is 0, we get minus k squared. So this goes down. If we take the eigenvalue with minus, it goes down even further, even faster, because there's the linear term. So it starts already with a negative gradient, and then it goes down. But if we take the positive plus here, then this guy goes down, but this guy goes up. And for small value for k, the linear term is stronger first. We go up. And then large values of k, the negative term wins. And one sees this function, it hits 0 when k is 4 times c. So we find a regime of small momenta where lambda is positive. What does it imply? let me call B plus the eigenmode. With lambda minus k squared plus 4ck, then my equation becomes, for that eigenmode, d0 squared b plus is the positive eigenvalue. And to make it now very explicit that it's positive, I write here plus absolute value, so it's really positive. And k is less than 4 times c. So what is the solution? Well, the solution is no longer an oscillation. The solution is I can have plus square root of lambda times t, or beta minus square root of lambda times t. And this is exponential growth here. So this is kind of a very famous problem or issue, that if one introduces a Chern-Simons term into the equation of motion, then there is a domain of momenta where there is exponential growth, and exponential growth we sometimes call this, to make it sound even more dramatic, we call it tachyonic instability. So now we did this. We closed our eyes. We introduced these chemical potentials, did a computation, found a funny term. Then we tried to analyze the funny term, and then we see that, well, if it's there, we get an instability. So now, what do we conclude from there? Well, in a way, there are kind of two possible things that one could conclude. Maybe the sort of the conservative conclusion. The first reaction is that we don't want that. It's bad. I mean, we wanted to look for a ground state, and now we found that we did everything correct, and then we find an instability. So it cannot be the ground state. Something is wrong. So we say that, okay, we want to get rid of this term. And now the way to get rid of this term is the same as we did with an abelian. Just say that the coefficient is 0. And in a way, it doesn't sound outrageous, because after all, we already said, at least for quarks, we think that there is chiral balance. And okay, the leptons, they also have Yukawa coupling, so there are transitions. So surely in an ideal world, at least the chemical potentials, if you can transform left-handed electrons to right-handed electrons, in an ideal world, if you waited long enough, you would have balance. And then you shouldn't introduce separate chemical potentials, and then this would be 0. So this kind of the conservative viewpoint. But now in cosmology, this is maybe too strong, because after all, at very high temperatures, everything happens very fast, and like the electron Yukawa is really very small, and these processes just don't have time to take place within the Hubble time that we may be observing. And so one can draw another conclusion. Or more interestingly, is that if we have chiral imbalance in leptons, then this implies, and in a certain sense, though I've only shown this implication, but somehow then we think that actually it's like equivalence is that, well, then we have this growth, we grow something. Well, what do we grow? We grow hypermagnetic fields. More specifically, we grow hypermagnetic fields with very small momenta, which means very large wavelengths. So if a chiral imbalance exists in leptons, then there are large-scale hypermagnetic fields. Large scale because small momenta. So now that brings me to my last topic. So this as such is not at all bad. Actually, maybe it's extremely interesting because apart from baryon asymmetry, apart from gravitational waves, these kind of large-scale magnetic fields it's a big issue it's a big-ish issue in cosmology as well. Well, depends, I guess, who asked. And so indeed, one can ask whether there is a primordial mechanism for generating magnetic fields. In this case, I would generate hypermagnetic fields, but then after the electroweak phase transition, I could convert them maybe to the real magnetic fields. There's a projection of the real magnetic or the electromagnetic field on the hypermagnetic field. So just like a couple of words about magnetic fields. The issue why they are maybe not as prominent, quite as prominently discussed as gravitational waves and baryon asymmetry is that is the observational side. I mean, in astrophysics, one observes magnetic fields all over the place, but it's difficult to deduce, like from far away, what kind of magnetic fields they are. What's the correlation length? If they are just like short-scale magnetic fields, like around a coil or some galaxy or whatnot, or a pulsar or something, or if they really are kind of large-scale fields which could point to a cosmological origin. This is very, my understanding is quite difficult, so I just put here a question mark. But of course, this is it's really something that people are working on very much, also because magnetic fields play a role in astrophysics. So in any case, from astrophysical motivations, one tries to understand magnetic fields on all length scales. And maybe at the end of the day, one is then also convinced that one needs a cosmological component in them. For the theory side, in any case, there have been many ideas about generating magnetic fields. And as also the case for gravitational waves and baryon asymmetry, basically you can take any epoch in the universe that we believe in, inflation, reheating, phase transitions, and then, however, certainly there are also magnetic fields which are related to astrophysics. And so that's really the key question, is how much of them are astrophysical origin and how much are then primordial. A little bit the same question as with gravitational waves. How much is from astrophysics, how much is primordial? These ones we would call primordial. Okay. Good. So I will not say anything more on that, but at least we saw now some indication that it's not that it's quite close to what we were doing, and conceivably one can find mechanism for generating very long wavelength magnetic fields in the very early universe. Then there's a whole discussion of how the fields evolve afterwards, how the wavelengths evolve, how the amplitude evolves. Is complicated. Magnetohydrodynamics, we were discussing a bit hydrodynamics. Magnetohydrodynamics is even a lot more complicated, but also very interesting. And so this is kind of a whole field of its own. But I wanted to mention it because it's not, even though the status is kind of, it's not like we could give here a clear number, like for the baryon asymmetry, we can really give a clear number which to explain. But nevertheless, it's an evolving field, and actually there is a certain community, there's a lot of work, also a lot of work on generating magnetic fields from phase transition. So it's good to keep an eye on that as well. Okay, I think that's essentially what I wanted to say today. I'll still come back to literature a bit, maybe if there are questions at this moment.
So, indeed, at high temperature, some small UKW are out of equilibrium, so you can set them to 0 in the effective theory. But eventually, before the phase transition, they come all into equilibrium, also the electron.
Yes.
So the coefficient goes to 0. This means that you have no more the growth of the magnetic field. But there is no way they can decay. They will be conserved, they will remain. Yes?
I think so, yeah. And so, right, yeah. Right, so indeed, yes, very good. So yeah, so this dynamics takes place actually much before the phase transition, and there you would have this chiral imbalance, you would generate a magnetic set of magnetic fields. Then also part of the magnetic fields can be converted back maybe to chiral imbalance. So it's complicated dynamics. People have studied it a little bit, but it's very complicated. I don't think it's very well understood. And yes, then the idea is that at some point the magnetic fields remain and the chiral imbalance goes away. Yeah.
Thank you.
I think there's a question online. I think, has this something to do with magnetic monopoles?
Magnetic monopoles, this has not to do with magnetic monopoles, no. I mean, magnetic monopoles, in the standard model there are none. And this was standard model physics, basically. Magnetic monopoles is an interesting topic, but a different topic than this one.
Yeah. When you talk about magnetic fields primordial,
yes.
This is the ordinary magnetic field or the hypermagnetic field?
So what we generated here was a hypermagnetic field, but we did this, I mean, much before the electroweak phase transition. Yes. These are hypermagnetic fields. But if the hypermagnetic fields are there, then at some point there's the phase transition, and then the massless field then the magnetic field is the electromagnetic field. But you know, the electromagnetic field has a projection on the hypermagnetic, or vice versa. So if you have a hypermagnetic field, then there is some factor of cosine or so. That component converts to the real magnetic field.
Okay, so thank you.
Okay. Good. So I wanted to just give some literature, some references. Okay, so maybe first it's a bit in, let's say, parenthesis, but like thermal field theory, there is, well, there are many books, but there's also one book which is also fully online in the archive, and that's actually some notes by myself and Aleksi Vuorinen. And so it's 1701 and then something. Then for what did we start with? We start with phase transitions. Phase transitions and gravitational waves. There are many reviews, but one I would maybe recommend is a review by Mark Hindmarsh and others. The others are students, because this was some school where he gave lectures, and then in that school the rule was that the students had to write up the notes. So you are lucky that you don't need to write up my note. 2008. Then baryogenesis. So with baryogenesis, the problem is, as I was trying to indicate, there are many steps which are kind of hard, and then there are also many reviews, but then in many reviews, then at one point or the other, there's lots of intuition is required. You have to believe this factor of unity and that factor of unity and some simulation which is not really explained or so. It's maybe not so satisfying if we're just learning something. But I think what I would recommend is a review by Dietrich Bödecker and Wilfried Buchmüller. It's 2009. Because this is sort of a little bit, I mean, this is phenomenology, it's not rigorous, but it's a little bit more less intuitive, maybe more solid equations than in an average review on baryogenesis. And then magnetic fields, also there's a review. For instance, by Tanmoi Vachaspati. And that's 2010 something. 2020 was a good year for reviews, it seems. Maybe people had lots of time in home office. Okay, and then in addition, for these lectures, I have some notes, and I wanted to fix a couple of things, but I'll put them on the page, like on Monday at the latest. So you will also get something from there. Okay, thank you very much.
Thank you, Mikko. Any questions?
I saw some papers in archive that try to understand some properties of dark matter using the connection with gravitational waves. Can you talk about a little bit about this topic, please?
I think From what you say, I wouldn't know exactly what the issue is. I mean, there are certainly many potential connections, many models which produce both dark matter and gravitational waves. Some mechanisms, for instance, okay, maybe the most obvious one nowadays, primordial black holes, you could imagine that they constitute part of dark matter and also produce gravitational waves. So I don't know exactly what the topic is. I mean, but yes, but the connection I think is model dependent. So there's no guarantee that dark matter physics, dark matter freeze out. So the normal textbook, weakly interacting dark matter freeze out, that does not lead to any particular gravitational signature. And the normal gravitational signature, well, a gravitational signature from a phase transition is not necessarily related to dark matter. But then there can be special phase transitions which produce both gravitational waves and somehow dark matter candidates, for instance. This is then a bit more exotic mechanism for dark matter, for instance. So it's very much model dependent, I would say.
Because I was thinking, what we see is only CMB. Before that, we have mechanisms to explain neutrino decoupling, freeze out of dark matter, and other things. I was thinking about some kind of event that generate the freeze out, for example, of dark matter, a WIMP, I guess. And I'm imagining a dark gravitational wave that is sensible to this event, and I don't know, like CMB sensible to the cross-section of the electron photon scattering. And so this put some kind of footprints in the profile of this gravitational wave. This is weird for you, or no?
No,
it
I mean
makes sense.
it's always good. In principle, it's good if you find a sort of a common explanation for many different things. That's always more. In principle, it's more appealing than taking all the mysteries we have in cosmology and for each of them finding a separate explanation. And yeah. But it's not guaranteed to be like that. So I mean, like, if you think about the lectures of Shaposhnikov, he was trying to explain everything, but he didn't have any particular gravitational signature, whether it's an inflationary signature, but nothing for LISA to find also. So it's also not guaranteed. I mean, that we hope to find something with LISA also. It's just a hope. I mean, it's no guarantee. So, but of course, if you find a model which is simple enough to be theoretically kind of convincing, and then it can do many things, then congratulations, that's great, yes, worth exploring.
Thank you.
Just to confirm, in the standard model, the idea is that this first condition would be actually satisfied anyway due to the Yukawa interaction. They would thermalize it via
yes,
Yukawa
if you take
rates.
Yukawa interactions literally, or in other words, if you go to a regime where these reactions really are in equilibrium, then it guarantees that you have the same number of left and right components. That means they are not separately conserved. Therefore, to begin with, you shouldn't even try to assign separate chemical potentials to them.
Thank you.
I don't know, maybe this is a naive question, but we are doing everything until now with the B hypercharge gauge boson, and then you conclude something about the hypermagnetic fields. But could you also say something about some electron, like other type of, not magnetic fields, but other signals? It's only hypermagnetic field.
Yeah, because electric fields in a plasma, I mean, you could talk about so in the U1 hypercharge.
Yeah.
I mean, there are magnetic fields, electric fields, but electric fields in a plasma, they always go, they go away. You know, if you have an electric field, you have free charges. So then the plus charge goes in one direction, minus charge goes in the other direction, and they annihilate electric fields. Electric fields are only on very short distances you can have electric fields, but large distances electric fields go in a plasma, electric fields go away. So plasma plasma is always, if you really like to take a plasma, then in the middle it's neutral. There are no, I mean, there are no electric fields. Everything charges go on the boundary. In the middle it's neutral, and the plasma in the universe is also a plasma. So electric fields, we don't think that they can be there at large length scales or large time scales. But magnetic fields, there's no magnetic. I mean, that's the reason why there are these huge magnetic fields in the astrophysics. There's no magnetic screening, or so you can really have magnetic fields. They stay there. In a plasma, they are frozen, and it's. One says they are frozen, meaning that they stay there for a long time. They can have long correlation lengths, and so.
No, thank you.
Yeah.
And then if you add another U1, for example, to the standard model and charge the fermions under this U1, for example, U1 B minus L or something like that, you also will have some kind of this prediction, like if you do the same computation, you also have a large scale, I don't know, hypermagnetic dark field that would be around.
Yeah, it's a good question. Yeah. So I mean, so in principle, whenever you have a U1, then you should ask what happens. Can there be long-range magnetic fields out of that? Theoretically, it's possible. They are not screened, as we say. But whether there's a mechanism for that particular model, I haven't really thought about that. Yeah.
Okay. Thank you.
Just to see if I understood it correctly, when we construct the standard model effectively, we get rid of these higher modes of the energy. And I was thinking about these magnetic fields. There are some regime validity also, or when we integrate over all momenta, we break at some point, or even.
I mean, the good thing was, if you remember, we only got this. These magnetic fields at small momenta. K was smaller than something, yes. And my C coefficient. This was actually it was proportional to the chemical potentials. In cosmology, chemical potentials are very small by themselves. Okay. So these momenta are really very small. Small momenta means small energy. So that's really the domain where our effective theory, if it works at all, it should work in that domain. It's the infrared, extreme infrared domain.
Thanks.
Okay, so I don't see any hands up. So thanks again, Mikko, for this beautiful set of lectures. So thanks for coming.